Right, good morning everybody, and welcome back to the next video that covers the stellar evolution section. And as you can see on the screen, the next part we're going to cover is classifying stars. Now, just a couple of slides I wanted to point out about the previous section. So in terms of a really good summary in terms of the life cycle of a star, what you see at the top is what a small star goes through, so starting from a nebula to a white dwarf, and a large star will go through a very similar process until the end of its life, and it will explode and become a neutron star or a supernova. And also there's a slide here which goes into detail about the important definitions related to this work. So hopefully those two slides will be of help to you when you're completing the questions on pages 11 to 15. But in terms of classifying stars, what you can see on the slide, on the picture there, is the constellation Orion. And normally when you look at this constellation at night, it might appear just as white dots, and actually they are different colors, and the colors can tell you the temperature. So if they're blue, they're very hot, and if they're yellow or red, then the temperature is much lower. So you can see here the difference in temperature. We're using the Kelvin scale of temperature, which some of you might not have met yet, but the ones that you see here in blue are at 10,000 Kelvin, and they are extremely hot. Well, I suppose these red ones are extremely hot, but these are 3 times hotter, and you can tell that by the color. So again, we use that idea to classify stars, and that's where we're going to lead into the a diagram which is called the Hertzsprung-Russell diagram, which makes a note of the star color and therefore gives us a guide as to what its temperature is. Now, just a note about these colors. In everyday life, you might think that something red was very hot and something blue was much colder, but in astronomy the colors work the other way round. So if an object is red, it actually has a much lower temperature compared to an object which is blue. So one way of classifying a star is by its temperature, but another way of classifying a star is its brightness. So the brightness of a star depends on two main things, as you can see in the bullet points here. Firstly, how much light the star emits, and secondly, how far away the star is. Now, you might think that the sun is actually a really big star, but it isn't actually, as we talked about before, that big a star. It's just the fact that it is so close to us that it looks so much bigger compared to the other stars. So, as I said, another way of classifying stars apart from the temperature is looking at the brightness. And you can see here, either this star here is very close to us, or it is massively bright, or perhaps it's a mixture of both. Now, how do we classify stars by their brightness? Well, the first person to try and do this was a Greek astronomer called Hipparchus, and he tried to do this a long time ago, 102 BC, and he came up with a scale that was called the apparent magnitude scale. Now, I'm just going to use the visualizer for this bit. And basically what he did was he used his eyes to classify the stars. and he went from a scale of 1 to 6, where number 1 was the brightest star that he saw, and number 6 was the dimmest star that he saw. So he would look at the brightest object that he saw, call it 1, look at the dimmest object that he saw, call that 6, and then classify all the other stars in between. Now, he was not using any sort of telescope. He did this all with his eyes, and it's called an apparent magnitude scale. So it's a little bit confusing, but 1 is the brightest and 6 is the dimmest. Now, since we started using telescopes, we obviously discovered things that are a lot brighter. And so now, when we use this apparent magnitude scale, they would be given a negative number. So if we find something that is even brighter, then we might give it an apparent magnitude of -3. And if we find something that is even dimmer, then it could perhaps have an apparent magnitude of 10. So we've got our scale of apparent magnitude, but we could have a star which has an apparent magnitude of 1, and that may well be because it is close to us, or it's a long, long way away, and it's very, very bright. So we need to find a way of comparing them in a fair way. And what we do is, so there's a picture of an eye, and I'm going to draw a line here. And what we do is we imagine that we bring them to a line which is where they are all the same distance away. And that distance is 32.6 light years. Now, when we get to A level and study astrophysics at A level, we talk about where this distance comes from, but just going beyond the IGCSE specification for a while, 32.6 light years. A light year is the distance that light travels in 1 year, and it's equivalent to 10 parsecs, which is another unit that we use in astronomy. But if we bring all of the stars to this point here and measure their brightness, then that gives us a stronger indication of whether they're big stars or whether they're small stars. So our sun is very close to us and obviously would have a low apparent magnitude. But if we actually take it to this point here, so we brought the sun to this point here, it would have an apparent magnitude of 4.2. And if you remember from the scale, the apparent magnitude scale goes from 1 to 6. So actually, on that scale, the sun would be a very dim object. So this is what we do. We bring all of the stars to the same point and we measure how bright they actually are. And so the term we use for that is called the absolute magnitude. And so that is a much fairer way of comparing how bright stars are compared to others. And when we classify stars, we will look at their absolute magnitude and also the other factor that we talked about, which is their temperature. And that will lead us on to the next section, which looks at those two variables, which is called the Hertzsprung-Russell diagram. Okay, now we've reached the end of the first section in terms of the introduction to classifying stars, And before we go on to the next section, which is the Hertzsprung-Russell diagrams, I would like you to have an attempt at this quiz, and you'll find it as an assignment on Teams, Introduction to Classifying Stars quiz. Just click on the link, it will take you to the quiz, and then when you've done the quiz, come back and watch the second part of this video. So we've talked about absolute magnitude, and that classifies stars by its brightness, and we've also talked about how temperature can also be used to classify stars, and we're going to put both of those things together. So I've drawn a graph here, and on the y-axis is the absolute magnitude, and on the x-axis is the temperature. So when we've looked at lots of stars, we might find that they have a very high temperature, and therefore they would be very bright. So a star like that, if it was a very high temperatures are over here, and if it was bright, we would put it over here. So these are unusual scales. Some of you might be looking at these numbers and think, well, these just don't make sense to me. But the way that these scales are increasing is what we call a logarithmic scale, and you'll do that at A-level physics, and certainly do it in maths as well, in terms of what we mean by logarithmic scale. So the absolute magnitude is a normal scale, it goes up in fives, but dimmer stars have a high absolute magnitude, and brighter stars have a smaller absolute magnitude. So this is a bit unusual in terms of how this scale works, and it actually, as well as being logarithmic, we've got the temperature going in the other direction. So it's a low temperature here, and a high temperature over here, and we use the units of Kelvin to measure the temperature of the star. So we've observed lots of stars, we've observed their temperature, and we've also observed their absolute magnitude, and we tend to find that 95% of stars tend to sit in this area here, and I'm using skittles to actually plot how they sit. Okay, and it would look something like that. So now, unfortunately, I couldn't get any blue skittles, so these ones over here should actually be blue. But the colour, if you remember from the beginning of this section, the colour of the star also tells us about its temperature. So the cooler stars over here will have a red colour, and as they get warmer, get hotter, their colour changes to yellow and then orange, and then the hottest stars we have are blue. But as I said, I don't have any blue, so I've used the purple skittles to represent that. So our sun would sit somewhere around here. So when I talk about this temperature, it's actually the temperature of the surface. The temperature of the surface of our sun is about 6,000 Kelvin, 6,000 degrees centigrade. And the temperature in the core is 14 million, quite an incredible temperature there. So whenever we've classified these stars, we've classified them by their surface temperature, and the sun sits somewhere about here. Whoops, just messed up my diagram there. So but we also have other stars which sit in this region, and we also have stars which sit in that region. And the objects that we find that sit in this region here are the red giants, and the objects that we find that sit in this region here would be the white dwarfs. So hopefully you're starting to see how this all fits together, and we can sort of plot how the life cycle of our sun will go. And if we say that it starts over here in a nebulae, then it goes there, so we'll call that point A, and then it forms our sun, which is point B, and then it goes into its red giant phase, which is point C, and then it will form a black dwarf, which is point D. So this is showing how our sun would move through the Hertzsprung-Russell diagram. So A over here is the nebulae, then the main sequence part of the life of the sun. Then it becomes a red giant, and then it would become a white dwarf at the end of it. So when we look at stars, and when we look at what their temperature is and what their absolute magnitude is, by plotting it on this chart, it can tell us at what phase of its life it actually is. So it's quite a useful diagram to have. And if we have a larger star, they would be over here. Larger stars have a higher temperature and they're brighter, and when they die they would move over to this part of the Hertzsprung-Russell diagram. Okay, where there are the super red giants. So what would then happen is that the star would disappear. Okay, it would end up going into a supernova, and it would disappear off the diagram. So this really is a useful chart, and as I said, 95% of stars would sit in this area here, and all of these stars are in their main sequence. So if we detect a star with a certain temperature and a certain absolute magnitude, and it fits in this region, we know that it's in its main sequence. And if we detect something which is very cool and not very bright, we can with great certainty say that it is a white dwarf. So quite an interesting way of looking at stars, and it's all built up from, you have to understand how a star goes through its cycle, understand what absolute magnitude is, and when you understand what those things are, you can then chart the life of a star like our sun using this diagram. Okay, so we've come to the end of this section of work, and what I want you to do now is do a short quiz, attempt a short quiz on the Hertzsprung-Russell diagram, and I've put that as an assignment in Teams. It'll be called Quiz on the Hertzsprung-Russell diagrams, and then when you've completed that quiz and submitted your answers, I then want you to go back to your workbook and answer the questions from pages 16 to 24 of the workbook, and that will take us then to the end of this section on classifying stars. Thank you.